Okay, I hope you already done all the problems on the two sample test. Okay, so come here, we just review this problem again, and the final exam there will be about 14 problems. Okay, maybe 15. Okay, and it takes much longer time to complete the final exam. So if you have no trouble to finish these 14 problems within, for example, within 2 hours, okay, and you should be okay, okay. All right, so our next problem we want to discuss is actually problem number 6. So we find there's a limit if it exists. If not, you have to prove it. Okay. So you take a look at this. This is a function. The numerator and denominator both have the same degree. Okay. So that means more likely that do not have a limit. Okay. So to prove it's not a limit, to prove the limit does not exist, it's much easier than to prove the limit exists. All right. To prove the limit doesn't exist, you just need to prove that along the two different passes, the function approaches two different values. Okay. So you can try, like this one, you can try the first pass, x equals t, y equals 0. Along that path, okay, and x squared y minus square, x squared plus y squared is going to be t squared minus 0 squared, t squared plus 0 squared, which is always equal 1. It approaches 1 as t approaches 0. Okay. Second pass, x equals 0, y equals t. Okay. Then x squared minus y squared over x squared plus y squared is going to be 0 squared minus t squared, 0 squared plus t squared. This is always equal to -1. Okay, so it approaches -1. Okay, as t approaches 0. So therefore, okay, the limit does not exist. I mean, the above limit, okay, does not exist. I'm not talking about the limit along the passes. The limit doesn't exist. The original limit doesn't exist. So that's much easier to prove. Okay. And for some other problems, think about this. Like, how about this? You can. Yeah, this one you cannot use the x-axis, y-axis. Okay, if you use the x-axis, y-axis for two passes, then the limit is always 0. So you cannot then conclude that the limit exists. Okay, so you need a choose a different passes. Okay, so the first pass, you should let x to be t, y equals t, for example. Then the second pass, you can let x to be -t, y equals t. Or it doesn't matter, when be x-axis, y-axis. So the limit will be different, okay? But so our next problem uses Stokes theorem to evaluate this line integral. Okay, so f is given x plus y, I, y plus zj, and z plus xk. Okay, C is a triangle, okay, with vertices 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay. So first of all, you have to recall, what is a Stokes theorem, right? The Stokes theorem is change the line integral to a surface integral. Okay. So you have to figure out the surface, what the surface you're talking about. The natural surface is a triangle, right? But it's not necessary. Sometimes, you can have a different surface as long as the boundary is a curve. Okay, so to solve this type of problem, my suggestion is you write down the formula first, the theorem first. Do not just start to work on that. Then you find out the run of the time. Then you stop there. Okay. Then you stop there, and even without mentioning what is Stokes theorem. Okay, so my suggestion is always write down the formula. Okay, so this is a formula, and this is going to be the surface and the curl of the vector field times ds. Okay. Then even you only halfway done. For example, find the curl of the vector field and find ds. Then you don't have time to finish it. You still get the partial credits. Otherwise, we don't know what they're doing here. Okay. So you have to find out the curl of the vector field. It's I, j, k. This is a partial derivative with respect to x, with respect to z. And here's x plus y, y plus z, z plus x. Okay. All right, the first term you're going to get, I think it's negative. I. Yes. The second term, W1, yeah, J, plus I think it's negative again. Yeah, negative 1K. So it is going to be negative 1, negative 1, negative 1. Okay, it's a constant. It's great. Yeah, I see. I got some requests about when is the test. Okay, the test start, final exam start at the same time, 9 o'clock. Okay, but you're given more time to complete. Okay, so you have to take it at that time. I will send the email to everybody later about the final exam time. It's not 3 hours. Right, so now you look at the surface. The surface is a triangle, right? The surface is a triangle. Okay, so to technically, to find the ds, right? This should be the a normal vector times ds, right? This should be equal to r use something like RV, you know, if you find that, okay, but if you find the parameterization for this, okay, but that will be too complicated. That's not necessary to this particular problem, right? Because the normal vector clearly is going to be 1, 1, 1 divided by square root of 3, okay? Okay, this is the plane, the normal vector to the plane. Okay, the equation for this surface is going to be 1, right? Is x plus y plus z equals 1. So you can write down the normal vector immediately. So therefore, this line integral, okay, is double integral of the surface, and this is going to be -1, -1, -1, and here's square root of 3, 1, 1, 1, right? And the still ds. ds is area surface element, so it's constant. So you will get 1 plus 1. It's a 3 over square root of 3, right? So that will be square root of 3 times the area of the triangle. Now, the area of the triangle, how do you find the area of the triangle? If we have an equilateral triangle, we discussed this problem before, similar problem. The edge length of the equilateral, it's an equilateral triangle, square root of 2. So we do have a formula. You can quickly get that if this side is a, the area is going to be square root of 3 over 4 times a squared. Okay, so therefore, the area of the above triangle is a square root of 3 here, square root of 2 squared. Okay, so the answer will be 3 over 2. Okay. But so the final exam, more likely, it's the time is proportional to the numbers of problems. So usually if I give 10 problems, right, then you are given 1.5 hours, because 15 minutes is for you to upload the PDF file. So more likely, if there'll be 15 problems, for example, right, and then more likely you're given 2 hours, 15 minutes. I have to double check that. Okay. Okay. So so we are given this line integral 3x squared plus 4xy, and that's a dx, plus 2x squared dy. Okay, where c is any path from the point 0, 0 to another point. Now show that this line integral is independent of the path and evaluate the integral. Okay. Okay. So basically, you want to prove that this is independent of the line integral. So when that happens, okay, if you have a px plus q dy, okay, and this will be, okay, this will be f of q minus f of p if the vector field is going to be the gradient of some function, okay, right? So this is a p that's point q in the xy plane, right? So when the vector field is conservative, and then the line integral is independent of the path. from one point to another point. Okay, as long as those two endpoints are fixed. All right, so all I have to do is just find the f, little f, right? So our p is going to be 3x squared plus 4xy. Our f, 2x squared. Okay. So how do we find f? Well, just integrate any of them, right? So if you integrate the second equation, right? And that'll be 2x squared dy. So that is going to be, its integral with respect to y, so it's 2x squared y, and the plus constant that depends on x, okay? Then you plug into the first equation, so I get 4xy and plus partial derivative of c with respect to x, which is 3x squared plus 4xy. And then I think this must be equal to 3x squared, okay? Then from here, c equals, I think, x cubed. It's plus any constant, but I just need a c, x squared, x cubed. So my function f is going to be 2x squared y plus x cubed, okay? So this is a function, okay? Then this integral of the function 3x squared, a line integral, right? Is going to be the difference of value of the function at the two endpoints. So those two endpoints, one is 1 and 2, f is 0, 0, okay? So the second one is 0, so the first one is 2 times 1 squared times 2 plus 1 cubed minus 0, right? So the answer is 5, okay? When you go over, when you redo the problems for the final exams, you don't look at my solutions. You know, you do it by yourself, okay? Then you try. You're trying to do it by yourself. You can look at the book. You can look at formulas. Don't look at my solution. When it's done, you double check it. Okay? Maybe you find some computation mistakes. Maybe it's possible. But don't not just always go just look at it without even thinking. Try look at my solution. Understand does not mean you got this idea. You will forget next day. You will forget. Okay, so that does not help you actually. Okay, that's my suggestion. I have students before always go to Mac and ask his tutors do all the problems for him. He completely understand. He completely understood all the problems, solutions. But when he came out to the Mac and give the same test, he couldn't do it, most of them. That's useless. Okay. You have to try and do it by yourself because this procedure, trying to figure out how to solve the problem will reinforce your memory. Okay. So if you find a solution, solve the problem by yourself, you will understand, you will memorize it. So our next problem is to evaluate this double integral, a surface integral ds. Okay. Well, S is the graph of z equals xy. Okay. Within, this is our typical problem. Within cylinder, x squared plus y squared equals 1. Okay. So to solve this type of problems, you needed to draw the picture first. Okay. I think I probably did this similar problem before. You know, at least the surface is similar. Okay, is z equals x plus y. Okay. Now it's possible if I change the problem a little bit, plus a constant, then I can move the surface above the xy plane. Okay. So right now somewhere xy is negative. Okay, x times y, like the second quadrant, third quadrant. Okay, z equals x times y, which is negative. It's below some, yeah, it's below the xy plane, but it doesn't matter. Okay, so we only consider surface. We're not talking about the the volume of the region. So, all right. So what are you going to do? Okay, now surface, some surface here, right? So you can draw the surface, a piece of surface. Right? For the surface, if you use a special parameterization, right? So this is a fxy, okay? Then ds is going to be dA, okay? But that one in the book, we already know that it is going to be square root of partial derivative of f with respect to x squared and plus fy squared plus 1. Okay. Okay, so that's it. You know, then you have x squared, right? X squared is the value of the function at the point x, y, z. At the point x, y, z on the surface is the value of the function is x squared. Okay, it depends on the first component only. So this S, okay, and the domains here is a disk, is a D, okay? So this x squared ds can be converted to the double integral, still x squared, okay? And the partial derivative of f with respect to x is just y. And this is x squared plus 1 dA, okay? Okay, so we are on the disk. Okay, this is the D. Okay, it's a x squared plus y squared less than equal 1 because it's within the cylinder, circular cylinder. So the graph is above this disk. So now what it can do, you're right, because the disk, so you do not use the iterative integral directly, you have to use a polar coordinates. The polar coordinates, yeah, there's no restriction. I is between 0 and 1, theta should be between 0 and 2 pi. Okay, it's a rectangle, right? So this is going to be from 0 to 2 pi, from 0 to 1. Okay, r is going to be r, x is going to be r squared cosine squared theta. What is inside is r squared plus 1. Don't forget there's r here, dr d theta. Okay, so you actually have two integrals here, right? One is with respect to theta, other one with respect to r. How do you evaluate this integral? You can switch the order, okay? But anyway, let's evaluate cosine squared theta first with respect to theta, okay? So this will be 1 plus cosine 2 theta d theta, okay? Now, cosine 2 theta, the integral over the whole interval from 0 to 2 pi will be canceled out. So what you get is only half of 2 pi, which is just equal to pi, okay? The integral of r squared, so actually is r cubed. Okay. This, you can use a substitution. So d equals 2r dr, okay? And that is going to be, Okay, here's from 1 to 2. Okay, and u to the 1/2. Now here's r cube. R cube is r squared times r, right? So that's why r squared, you still that's use u minus 1. And r and dr is half of du, okay? So that is, you take 1/2 out. And you will get u to the 3/2 minus u to the 1/2 du. Then you find the antiderivative of each of them. The first one will be, okay, this, and the second one will be, okay. Yeah, it's harder to simplify it, and if you don't have a time, don't even try that, because it's just a waste of time. Okay, you should finish as a problem, but at least you have to write down the following. I think that, let me cancel 2 first, right? 2 cancel out. So there's no 2 here. So the first one is 1/2 2 to the 5th, okay, minus 1/3 and 2 to the 3/2, minus 1/5 minus 1/3, okay. When we after plug u 1 for u, then u to any number is 1, okay. So we leave it like that. Okay, I'm not going to finish it. Okay. So we always have a problem called find the angle between 2 planes. Between 2 planes, okay? X plus y minus 2z equals 1, and negative 2x plus y plus z equals 1. The idea is as follows. Okay, if you have a 2, this is a 2 plane, right? You look at this from this angle. So you're looking for the angle theta, or doesn't matter. So an angle between them, right? You choose an angle smaller than pi/2, because there's another one here, theta prime, right? Which one you're talking about, right? So we're talking about the angle theta. So theta should be between 0 and pi/2. Okay, the smaller one. Okay. So in that case, how can I find it? Okay. So each tangent plane there is a normal vector. So using the normal vector, this is a normal vector, right? The other one, we don't know. Maybe this is this is a perpendicular, and here's another normal vector. Okay, and this angle is a theta. Okay, but if it happened to be you choose a different direction, this will be theta prime. Okay, so it's possible you don't know which 2 normal vectors form an angle between 0 and pi/2. So if you get if you get a cosine, you see the relationship between cosine theta and the cosine negative theta is going to be negative cosine theta, right? Cosine prime. So that's different. So if you get a negative value, you can still get positive value. Okay, that's a relationship. Okay. All right. So now the normal vector for the first plane is n1. It is going to be 1, 1, negative 2. You can read it from the coefficients, negative 2, 1, and 1. Okay, those are the 2 normal vectors. Okay, based on their coefficients, you can look at it from their coefficients. You can get. Okay, so that's a normal vectors. Therefore, cosine theta or cosine theta prime is going to be n1 dot n2. Okay, so let's do the computation. So inner product of those two is -2 plus 1, -2. Okay, well, I don't know what's always. Okay. And and the first one is going to be 1 squared plus 1 squared plus -2 squared. Second one is -2 squared plus 1 squared plus 1 squared. So it's going to be -5. And here you are going to 4 plus 1 plus, that's a 6. Okay, so 6. Yeah, so it's a negative. So that means the angle we find out is not the angle between 0 and pi over 2. Okay, so then we say cosine prime is going to be 5 over 6. So this should be the angle we're talking about. Okay, it's between 0 and pi over 2. Yeah, so the angle we got here, yeah, this is a theta, actually now theta prime, right? This is theta. And we get the angle larger than pi over 2. This still angle, it's between two planes, but that is larger than pi over 2. You find the one of them, it's fine, okay? Now, if you think about that, if you just write, yeah, you can say arc cosine. Well, yeah, if you use a negative value, you will get an angle bigger than pi over 2, okay? So our next problem will be use the divergence theorem to calculate. So I already tell you have to use the divergence theorem. But if you don't use divergence theorem, if maybe I do not mention that, okay? So I just say evaluate this surface integral f ds. Okay? F is going to be x, y, z squared. I have 3 components. S is bounded by, yeah, S is the surface of the solid. Okay, and this solid is bounded by upper hemisphere is bounded by x squared and I don't know, I always insert some things to the, okay, it's bounded by x squared plus y squared and plus z squared equals 1 and z equals 0. Okay. So there are 2 surfaces. There are 2 surfaces here. Okay. So step 1, you draw the surface. Okay. So it's closed surface. So S is a closed surface. Okay. So in that case, even without mentioning the divergence theorem, you should, if it's closed surface, okay, you should use you should use a divergence theorem. Now sometimes, okay, sometimes you make it as closed surface. The reason is, okay, if I just say S is upper hemisphere, yeah, I'm talking about this a little bit later, okay? So let's use a divergence theorem. By the divergence theorem, okay, this surface integral becomes the triple integral. Okay, so the triple integral I can put B here. Okay, so divergence of f and the dv. Okay, so just compute the divergence. The divergence here is the first term is going to be partial derivative x with respect to x, partial derivative y with respect to y, and partial derivative z squared with respect to z. Well, it is going to be 2 plus 2z dv. Okay, 2 plus 2v dv. Okay, the next step is, because this is an up hemisphere, right? So you should use polar coordinates. We call spherical coordinates. Rho sine phi cosine theta, y equals rho sine phi sine theta, z equals rho cosine phi. So phi is between 0 and pi over 2. That's a key point, okay? Because this is angle phi, and phi cannot be larger than pi over 2, otherwise you go to the lower hemisphere, right? So theta is no restriction. Rho is no restriction, it's going to be greater, right? All right, that's the setting up. All right, so now, now you got, you have to use this new coordinates, okay? So this is a triple integral, okay? All right, so so the next step is just you can, doesn't matter, because this is a rectangular box, so it doesn't matter which one you put first. You can say, let's put a row here from 1 to, right, then from 0 to pi over 2, from 0 to 2 pi. Okay, then be careful. The one outside will be the theta, then the phi, the rho, right? All right, so here's 2 plus 2z is a rho cosine phi, okay? And then the part from the derivative will be rho square sine phi. Okay, that's it. And that's independent of theta. So my opinion is just you can take 2 pi out first. Okay, so you will get, another 2, have a factor 2, have 4 pi. So I get 1 plus rho cosine phi, rho square sine phi, d rho, d phi d rho, okay? All right, what is the next step? Well, you can multiply this out, rho square sine phi, and here rho cube sine phi cosine phi. Now sine phi cosine phi can be written as, this can be written as sine half 2 phi divided by 2, okay? So the antiderivative of the above one will be negative rho square cosine phi, okay? And also have a negative divided by 2, so divided by 4. Okay, so this is antiderivative, and let's try to complete. All right, when you plug pi over 2 for 3, the first term will be cosine pi over 2 is 0, but the second term is not going to be 0. Okay, cosine pi is going to be negative 1. Okay, then you plug 0, cosine 0 for phi, right? And that is going to be a quarter of this. okay, 0. Okay. All right, so let's simplify a little bit, okay? I have a negative rho square, so I have a rho square. So I have a positive quart. I think it's both are positive, negative, right? Minus, yeah, negative. Yeah. So actually it's going to be half of rho cube. Okay, this will be positive, okay? Because I have a positive quart and here negative, negative also becomes positive rho cube, okay? So then you have antiderivative of 1/3 rho cube, and here is going to be 1/8 rho to the 4th power. And finally, I got, okay, so that is answer. All right, now let's go back to this problem again. What happens if I only give you the surface? S is just the upper hemisphere. Okay, and I want to evaluate F is still going to be X, Y, Z squared. Okay, so evaluate this surface integral. Okay, how do you do that? Okay, question, right? Okay, there you cannot apply the divergence theorem directed to this problem. S is not a closed surface. Okay, S is not a closed surface. So there are a couple ways to do this problem. Now, if we are lucky, okay, let's say the bottom part I call the S prime, okay? This is S, right? You take a look at S, okay? You take a look at this one, okay? And this one, this is actually is going to be S prime. F is become special, okay? X, Y is 0, okay? Right, because the third component must be 0, it's in the XY plane. Okay, and then the normal vector is to point to downward. It's going to be 0, 0, -1, and then ds. And find out this is going to be 0 and ds. So it's 0. So it's 0, nothing there. So therefore, this surface integral, you can add, you add a 0 part. Okay, so now this surface become a closed surface. Then you can apply the triple integral. Okay, this is going to be E and the divergence of F dV. Okay, then you get the above result. It's going to be 4 pi 1/3 plus 1/8. Okay. Now, if it's not equal to 0, you still can easily compute it. Then that's okay. Okay. For example, if I change it, yeah, then you just add because this part can be computed easily. Then because it's on the disk, right? The normal vector is easy to find out. Then you, as long as you consider that part added to the original integral, then you still can use a divergence theorem. This is a more tricky problem, okay? You can also parameter the surface directly, use a surface integral. It's not too bad, okay, because it's easy to find as a normal vector, okay? Yeah, it's easy to find the normal vector. So for example, here's a sphere, the normal vector n at the point x, y, z, n is going to be x, y, z, right? So the surface integral, this surface, f dot ds is going to be surface integral f dot n ds, right? So, okay, n dot x, y, z ds. So you end up with x squared plus y squared plus z cubed, okay, and ds, okay? Well, on the surface, on the sphere, you always have this. So x squared plus y squared can replace by, even can replace by 1 minus z squared, z cubed, ds. So you still have to parameterize the surface as a sphere in order to complete this, okay? I'm not going to come. It's a little more complicated than you thought. Okay, you have to parameterize a sphere, and then you end up. Yeah, it's a surface integral. Okay, you have to. It's more complicated, as you can tell, that without using divergence theorem. Okay. Okay, so I stop here. Okay, so let's take a look at the next problem. Find the area of the surface this surface is given by a pretty strange function. And it lies and the first octant. All right. So first octant means here, right? This portion. Okay. All right. I just draw a quarter of the cylinder. And x, y both are positive. So here's there. I think the surface looks pretty strange surface. Okay. It could probably goes like that. Okay. And it's above this disk. Okay. It's harder to draw it, but when x equals 0 to 0, okay? Yeah. No, my drawing is wrong. Okay, I need to reschedule it. Reschedule it. Why? Because I want to find out where's the point, right? Let's use a red pen. Okay, when x equals 1, y 0, it's here. When y equals 0, y equals 1, x equals is here. Okay, so the graph looks like that. Okay, this is a circle. Okay, it's kind of aloof above that. But this is a graph, right? For the graph, the area of the surface area is just as a double integral on the D. You can write down this formula right away. Okay. What happens here is just as an integral. You can get this formula using the parametrization of the surface of the graph. Okay. So this is that's all you need, right? Then you evaluate this. The derivative of f with respect to x is 3/2, x to the 1/2 square, 3/2, y to the 1/2 square, and plus 1, and dA. and turns out to be just equal to 9 over 4. Here's x plus y and plus 1 dA. Right? Yeah. X 3 over 2 minus 1, it's 1/2, then squared. Okay. So I'm not sure we are able to evaluate this integral. Okay. So let's see. Okay. So you have to, right? This is x-axis, y-axis. So natural way is to use a polar coordinate, right? Polar coordinate. So it's going to be, x is going to be r cosine theta, y equals r sine theta. Okay, so the integral here is from 0 to pi over 2, from 0 to 1, right? And here's 9 over 4, and the x plus y, we have trouble here. R cosine theta plus r sine theta, and plus 1. When dA should be just RD, dRd theta, okay? All right, now we have problems. Okay. So let me rewrite it again. Okay, it's 9 over 4 r cosine theta plus sine theta plus 1 RD dRd theta. How do we solve this in code? How do we evaluate? Think about it, okay? I don't like the radical, right? It's too complicated. If without the square root, I can do that. Okay. Well, maybe we still can solve it. Okay. Let u to be 9 over 4 r cosine theta plus sine theta and plus 1. Okay. I'm trying to make it special. Okay. So du equals 9 over 4 cosine theta plus sine theta dr. Okay, not too bad, right? I'm not sure. Yeah, I'm not sure I can evaluate it. So let's double check. Is this the right problem? No, right? So yeah, lines was called. It's about surface integral. Yes. Okay. So from 0. So when I equals 0, this is just 1. When I equals 1, it's 9 over 4 cosine theta plus sine theta plus 1. Okay, and here's u to the 1/2. How about r? R is going to be equivalent to u minus 1, but you have to divide by the constant, right? You solve for r. So from here, you have to solve for r. U minus 1 divided by 4 over 9. And I think I have the term in the denominator. And then du, okay? Well, we can find the antiderivative of this, but I don't think we can evaluate, okay? Now you can, this is the theta. You do get you evaluate with respect to u, no problem here. But how can we get rid of, how can we deal with the sine theta, cosine theta? Okay, so this end up with this polar coordinates leads to a very complicated integral. Okay, polar coordinate leads to the very complicated integral. Okay, right? As you can see that. Is there any other way you can try? Well, use the iterative integral. Maybe you can work out. Okay, so we stop here. Okay, it's too complicated. Okay, so we go back to. You go back to this integral. Okay, 9/4, right? 9/4 x plus y plus 1. Okay, we try different. Otherwise, you just leave like that. Cannot do it. Okay, okay, it's not always, always you can find exact value for any surface. Okay, so this is double iterative integrals. It's x is from 0 to 1, right? But the y is between these two. Okay, so it's going to be integral from 0 to 1 minus x squared, 9/4 x plus y plus 1 dy and dx. All right, well, you can evaluate this integral, okay? So you can, let's see. So this time the substitution is a little bit easier. Okay, you use this substitution, du equals 9/4 dy. Okay, we view x as constant. Okay, so that means the antiderivative and actually the antiderivative of that function. You can use substitute directly, or you just find the antiderivative of the inside function with respect to y variable. Okay, so let's see. Okay, I'm going to evaluate u to the 1/2, right? And since du equal that is going to be 4/9 du, right? So the antiderivative is 2/3, u to the 3/2, 4/9 plus 1. Okay. 8/27. And then u to the 3/2. And why is there constant here? No constant, plus any constant, okay? So this is 8/27. And then you put the u back, 9/4 x plus y plus 1. I think we're still not able to evaluate this integral because we find the antiderivative of that function. It's a 3/2. But when you differentiate, yeah. So when you take the difference, right, you replace y by the above number, so you end up with 8/27, okay? This is going to be 9/4, and x plus square 1 minus x squared plus 1, okay? And minus 9/4, x plus 0 plus 1. All right, so you have to stop here. Anyway, this is a function we are not able to evaluate the surface integral with the traditional method. Okay. Of course, if you use a computer, that gives you the estimate of the value. Okay. The reason is if it involves the square root, right, radicals, it's very hard to get rid of the radicals. Okay. Yeah. If I change the problem to z, yeah, what happens if z equals x to the 5/2 plus y to the 5/2, then we are okay. Okay, use polar coordinates, we are able to solve it. Then okay, then you can find out Okay, so it really depends on the function you are given. Okay. This will be okay. Yeah, you can try this. Try this at home. Okay. So I needed to, yeah, I have to modify this problem sample exam. Okay. So we let function to be x squared y plus y squared plus 4xy, or plus just 4y. Okay. Find the local maximum and minimum value, okay, of the function. If there's any center point, you point out the center point. Yeah, indicate the center point. Okay. All right. So first of all, you find the critical value, right? Find the critical point. So you partial differentiate the function with respect to x. You get 2xy, and that's it. That's no other x. Here's x squared plus 2y plus 4. Yeah, plus 2y plus 4. So you set this to be 0. You're trying to get critical points out. Right? Now, be careful when you solve this. Okay, which one you should start? X times y is either x equals 0 or y equals 0. So it's a case 1. X is 0. Okay, by the first equation, right? If x is 0, then 2y plus 4 equals 0. So y equals -2. So you get 1 point. Okay, case 2. Y is 0, right? So the first equation is always satisfied. In that case, x squared plus 4 equals 0. No solution. Right? X squared cannot be. Cannot be negative. Of course, if I change the function, I change the positive 4 to the negative 4, then you have 3 solutions, okay? Because you get x squared equals plus minus 2. But right now, it's x squared plus 4 equals 0, so no solution. So that makes it easier. So only one critical point, which is 0, -2, right? All right, so now you have to find the matrix at that point. It's 2y, right? fxy is 2x. And that is also, it's going to be fyx. Then fyy equals 2. Okay, so that means the matrix at the point when x equals 0, y equals -2, I'm going to get -4 here. X is 0, 0. I get 2 here, right? So clearly the determinant is going to be -8. It's negative. So that means it is a center point, okay? 0, -2. Yeah, so you got center point. Okay, the center point is a 3-dimensional space. So I have to say where it is, right? When x equals 0, y equals 0. So you got center point. Center point. You can say at 0, -2, okay? So the point has 3 components. So when x equals 0, y equals -2. And I think it will be -2 squared plus 4 times -2. So it's 4 minus 8, so it's -4. Okay. Yeah. So coordinates. All right. My almost the last problem, right? Given the point 2 pi over 6, -2 square root of 3. Yeah, this version of the final exam is very similar to the previous one, right? Okay. So we want to change from cylindrical to spherical coordinates. So this problem is you want to make sure you understand the coordinates, those special coordinates. Okay, if you can do the conversion, then that means you understand that. Okay. So let's understand the cylindrical coordinate. How do we get the cylindrical coordinate? It's in the system, right? So here's this essentially is a polar coordinates. Okay, here's x, y, z in, okay, and this is theta. Okay. So this will be r, right? So here, x is going to be r cosine theta, y equals r sine theta, and z is still equal to z. Okay, so that means r is going to be r squared is going to be x squared plus y squared. Okay, for the spherical coordinates, it's a different way to do. Okay, this is a yeah, r is here, and this is a row. Yeah, still get r, but this will be phi. Okay, and then this will be angle theta. So so x is going to be still r cosine theta, but the I is a sine phi. Okay, y equals r sine theta. This is r sine phi sine theta. So z equals r. No, z is actually just is a row cosine phi. Okay, so yeah, how do you get the z? Right, z is here, right? So row cosine phi gives a z variable. Okay, so actually for the same point, the theta will be the same, right? If you look at the picture, right? So theta will be same. So maybe we have a better way to solve the problem. Right? We have this one is a 2 pi over 6 -2 square root of 3. Now, so theta here, it's the same theta, right? Clear from the picture, should be the same theta, right? So here's a theta, we already got theta here. Theta here is a pi over 6, and that should be also pi over 6. Okay. And I is a 2. Okay. I is a 2. So how can we trying to figure it out quickly, right? So I is a 2. Yeah, what is a rho? Okay. Rho is this distance, right? Now, if you look at the triangle, this is right, the triangle, right? If you know this side is R, right? So from here, I can tell that rho is going to be square root of z squared plus r squared. Okay, here's r is going to be 2. Why? Because it's a right triangle. If you understand where is r, right? So then by the Pythagorean theory, to this right triangle, here's a z, right? ZR and a rho. So you can get z components is going to be, yeah, I is actually 2 square, right? Z is going to be 2 square, 3 square, okay? So I will get 4 plus 12, so 16, 16, the square of 16, 4, okay? So that's another way to do. So you get rho, and then the phi is much easier to get, right? Rho is I is going to be 2, okay? I is going to be 2, right? Rho is going to be 4, then, and clearly phi should be equal to 30 degrees, right? So you have a triangle here. Rho equals 4, I equals 2, that's a phi, right? So phi should be equal to pi over 6. So you get all of the information you need, okay? You just do the comparison, you know, with two coordinate system with the same point. I'm talking about same point, and R here is R here, right? Theta is the same theta. So the theta for the cylindrical coordinate systems is the same theta for the spherical coordinate system. Okay. Okay, so this is a geometry, okay, 3D geometry. Okay.